Yeah, so today it was about, so this was about sensitivity analysis and duality. So if we look at the first question, I'll skip this group because I didn't want to. So if we actually change the capacity of plant 2, let me just do this in a bit. Yeah, so plant 2 from 12 to 18 hours, recalculate the new optimum, and using the fundamental insight. In that case, basically what we can do is we can simply multiply the shadow price, Y star, with the new right-hand side, and that should give us our new right-hand side. Or in this case, no, sorry, so we can actually do we take our modified, our modified B, so we do multiply by B minus 1, and there we basically get our new right-hand side. So we can simply recalculate our new right side, and if you want to find this, and this is on page 180 something, let's see, should have a book I gave to Mahela actually did have notes in it. Somebody asked me if it was okay to make notes in the book. I'm generally okay with that, but don't write into it. So if you just put a post-it or a marker in there, then keep the book nice. So don't ruin it by writing it. So yeah, so it's the B star is B minus 1 times B, and actually if you want to recalculate the new objective, then what you have to do, of course, is basically take, in this case, the shadow price for that constraint, which is 1.5. We increase it by 6.
The after deadline link of lecture 3 is not there.
I'll make it after. Is that okay? I forgot to add that. Then you can start after. I'll do it right after the explanation, and then, or do you want to see it while? Or shall I add it now, or shall I do it later?
Yeah, I prefer now, but I don't know.
No, I'll add it. I'll add it in a moment. I forgot to add it. That's good. That's a good one. I'll do it right after the explanation. So if we know 1.5 is a shadow price, then basically it will increase with the increase in production hours times 1.5, so we'll get to 45. Now if we increase it even more to 24, then we can actually calculate an optimum. In this case it will be 54, so again 1.5 times 12, in this case added to the original 36. So it's even higher. However, now if we calculate our new right-hand side, what we find is that actually we actually have an overproduction in plant 3 by 2 hours. So we're actually using plant 3 for 2 hours more than we can. And what basically happened is that our corner point solution, which had our initial optimum, was actually shifted outside the feasible region. So this corner point has become an infeasible corner point. And it still fulfills the optimality criterion, however, it's infeasible. So that means that we actually have to look for a different corner point to find a feasible optimal solution. So if we actually look at Z is 45, so I'll just go back here to here. So yeah, so well, we can recalculate the new value. Oh yeah, what's also interesting to note here is that we see actually, in this case of 45, we see actually that we have, what is it, x3, here, so it's 490 in case of this upgrading to 18, and what you actually see is that in this case it's this is actually the correct answer. You see that x0 is basic, but it has a value of 0. So basically we have a basic variable with a value of 0. So that can happen. Normally it's the non-basic variables which are 0, but a basic variable can also have a value of 0. What it actually indicates is that we have 2 corner points at the exact same location. So now we actually, so basically we have 3 constraints in this case, because we have a 2-dimensional problem. We have 3 constraints crossing at exactly the same position. So basically it means that we have actually 2 or even 3 corner points in exactly the same place with exactly the same objective value. Yeah, so if we then re-optimize it, then actually what we get is now we get we get the same solution, 45. So we get x2 is 9, x3 is 4, and x4 is 6. So it's still the same solution basically. So we still have x2 is 9. In this case, actually x1 is 0, this x1 is 0. So x1 is still 0, but now x1 is actually gone from being basic to being non-basic, and now x3 and x4 are basic. So you see, we now have 4, 9, what is it? And we have a different 4, 9, 6. So we have a different corner point solution. However, x2 still has the same value, so it's still the same optimum, but it has a so it's a different corner point. And that's basically what we get after we've made it, solved it again. Now, if you want to do sensitivity analysis, then what we can do is simply, we know that our right-hand side has to, everything has to stay larger than 0. So in the case of B1, because it's only basically on the left-hand side of B, so we see that that only affects the right-hand side of our top constraint. So basically, if we then fill in 4 plus the delta, and we multiply it, we get this. In this case, that means that B1 is not allowed to reduce with more than 2. And as B1 is initial value of 4, this actually means that B1 has to remain higher, at least equal to 2. So if B1 becomes lower than 2, then this one will actually become negative, and thus will become infeasible. Now, if you actually look at B2, then B2 actually appears in all the constraints, because B2 basically is multiplied by all these factors. All these constraints have a factor of B2, and actually this constraint has a negative factor of B2. So that means we both have an upper bound and a lower bound. So in this case, what you see is 2 plus 1/3 times delta B2. Well, that means that in this case, if B2 is reduced by more than 6, in this case, half times B2. So if B2 is reduced by more than 12, so 6 is the most one. So delta B2 is not allowed to be more than, well, let's say less than -6. And here, actually, because we have a negative coefficient, it actually means that if B2 actually becomes increases by more than 6, this constraint will be violated. Yeah, so as B2 has an original value of 12, it basically means that B2 is allowed to go from 6 to 18 for this corner point to remain feasible. Is that clear? Yeah. If we actually look at the new solution, so we basically have the two corner points in the same location. So for the 18 case, actually we have both corner points in the same location. Another thing why you can see this by, let me just grab this, is if we take the window problem, I actually don't have it printed here, then actually what happens is that our that basically constraint 3 has a factor. So constraint 2 and 3 are actually the same, but constraint 3 also has an additive factor times x1. So actually you can see that for a certain value for x1 is 0, these will actually interact. These will have the same value. If we actually look at z star, then we can simply recalculate the z for 1, which is what it has to become. So if in this case, if we do y star times a, we can calculate it 7.5. We know that z1 minus c1 has to be equal to 0 for it to become basic, so that has to be higher than 0, and that will happen for c1 of 7.5. So if we increase the value to 7.5, or increase the cost coefficient to 7.5, then actually it will start to become interesting again to solve it. And actually what happens in that case is that our objective value runs parallel to constraint 3. So actually in that case we'll have multiple optima. So if C1 is 7.5, we will actually have multiple optima. To get back to this, so we actually have two corner points in exactly the same location. So we have two different tableaus with both with a z value of 45. And what we see here is that, x2 has a value of 9. x1 in this case is basic, but is 0. In this case, x4 is basic, but is 0. So, but x2 is still 9, x3 is still 4. And these solutions, corner point solutions, are in exactly the same location. If we look at the assignment 3.2, let me just go here. Okay. Question 2. So if we look at assignment 2, actually here we start here with the dual problem, as you might have noticed, and we want to make the primal problem out of it. So if we solve this problem, then we need quite a few variables. We have 4 constraints, and because there are larger than or equal constraints, we need artificial and surplus constraints. So we need 2, let's say so 2 extra variables per constraint. So basically 4 plus 4 times 2, so we actually need 12 variables to solve it. So it becomes quite a large problem. So, well, if you then calculate y1, y2, then disappointingly it becomes 1, 1. So we can solve it, and I won't show that. I'll put a file on the right there where you can follow it, but you can imagine, well, if you've done it, it's quite a lot of work, and then you get the solution 1, 1, which is a bit disappointing. Could have been the code for your bicycle lock or something. But then, of course, if you switch to the primal problem, then also what you see is that, of course, it should be a maximize, not a minimize. So if we go from this problem to the dual, in this case we have a minimize, then of course for the dual problem it should be a maximize, and then of course we form it through the standard rule. So basically what we got is 4x1, 2x2, 1x3, 1x4 has to be smaller or equal to 5, and the same goes here. So we basically end up with these. A mistake made actually. Yeah. Just look at that one. Good. Yeah. Here. Are you saying 2x4? So it's 4, 3, 1, 2, and this is 4, 3, 1, 2. Yeah, you're correct. Yeah, indeed. Yeah, so that's something I never made with making these slides. I'll just add it here. Yeah, good one. So that should be 2x4 indeed. I think it was actually correct in the question, right? Here, oh no, here it's also wrong. Okay, good one. Yeah, so that should be 2x4. So it's so if you want to solve this one, it's actually a lot easier because we only need 4 decision variables and we only need to add 2 slack variables. So we only have 6, which we need to solve. So our simplex tableau is actually a lot smaller, so it's a lot easier to solve. Well, what are then the optimum values? I think I've given them. So actually, for the optimum values, we can simply look at the reduced cost of the first problem. And if you look at the statements, then actually they're both true. So if we just look at row 0 for the decision variable, then the primal is equal to the values of the surplus in the dual and vice versa, and also the shadow price for the primal problem is equal to the solution of the decision variable for the dual problem. So this is one of the basic rules we can use to analyze it. So I'll make sure this is actually also corrected in the question. So it's a good catch. So we can just solve it using the standard method, and we get this answer. So 3.3 here, actually we go back to the what is it? The Union Airways example. We would basically have to accrue the check-in desks. We solve that and create a sensitivity report. Okay, what do we see there? And this, of course, is getting more if you're actually going to create a big problem. You're not going to solve it by hand. So in that case, you will use a solver. In that case, of course, you have to be able to interpret it, and that's what we're doing with this assignment. So if we look at the table, which is here, then actually what we can see here is that we get an allowable decrease, in this case for x1, so this cell corresponds with x1, and we have an allowable decrease of 10, so that's actually our, let's say that's actually the limit, so that's actually the change there. So if this decreases with more than 10, so the cost decreases more than 10, then what happens is that in this case, this one will actually become, then our solution will change. have a bit of a cold today, so. If x6 and x15 are the surplus variables, which of these are basic? Well, larger than 0. Well, actually, if we look here in the table, and actually if we look here, we can see our constraints here. And what we can see is that in this case, actually, so these all are non-basic. So these constraints basically have a select variable which is equal to 0. Same as for these. And these one actually will have a select variable larger than 0. So for these constraints, the select variable will actually be basic, and for the others, it will be non-basic. Also, when you're looking at this example here, which one is wrong? Well, if you look here, then this is the given answer. And of course here, if you correspond it, then you know that actually in the last case, it should actually be, let's say, for this one, it should actually be this one and not this one. So because this basically contains the the surplus variables for the the surplus variables for the original solution, then actually this one should be -1 and this not. Yeah. So it's actually column what is it? It's column 9 in this case. So, well, using MATLAB to invert, again, a matrix like this, if you have to invert it, it's not a very easy task. So, yeah, so it's a lot of typing work. So you probably want to automate that. So if you invert this, then you end up with this matrix. And now, if we recalculate our B star, then what we can actually do is we just multiply it by B, and then we get this matrix. And now, if we look carefully, then we'll actually see the values here coming back. So what we see here is that we have 48. Let's see, we have oh yeah. So for some we'll actually have here we have these. For the basic variables, we'll actually have our right hand sides, which are so we'll actually have our shadow prices. So that's actually our allowable decrease. So 48.6. And for the other ones, we'll actually have our for the basic variables, we'll actually have our values. So that's 48, 31, 39, etc. So you'll actually see these values coming back. Okay, now here if we want to do sensitivity analysis, of course, it becomes a bit more complex. If we do it here, of course, there's lots of ones and zeros. So if we then fill in the delta B1, then we end up here. And what we, of course, here can check, if we now look at delta B1, in this case, it could be -48. In this case, it can go up by 31. In this case, it can go up to 6. So it may not increase with more than 6, and it may not decrease with more than 48. So basically, B1 can be between 0 and 54. And if we look at delta B3, then in this case, again, it only comes back in the single, for the single constraint. So in this case, what it means is it can only increase by 14, so it must remain smaller than 79. And of course, then if we look on the right-hand side, we see here the shadow price, and of course, the shadow price are the values of the decision variables in the dual. So this is the shadow price. So if we'll actually look at the dual problem, in which case we'll have 10 decision variables, then this will actually be the solution for the decision variables. So that's much faster than solving it. 3.4. Let's see, 3.4. Here, so we have this problem, and we define the slack variable. We've solved it here. So even here you get a solution. Well, the basic variables, how do we determine that? Well, the basic variables, again, this is a very important thing. The basic variables should never be in your objective row. So it's basically the variables missing for your objective row. So in this case, that's x1, x2, and x6. So already know that. If you then look at your constraints, you should look at where they have a value of 1. So in this case, it's x1 or x4. Well, x4 is not basic, non-basic, so it's x1 in this case. In this case, it's x2. So it's x2, x6, x1. So it's yeah. So it's x2, x6, x1. So that is the correct order in this case. So x2 is given by constraint 1, x6 is given by constraint 2, and x1 is given by constraint 3. Well, why is this order so important? Well, if we have CB, which is the coefficient of our basic variables, which we have to multiply by b to the power of -1, so the inverted B matrix, then we need to know the coefficients in the original, but also their order. So we also need these to get the order correctly. So here, of course, then we have our solution x2, x6, x1. If you put it into the ORI tutorial, it will already give you this order. But again, you can also reduce it by, first of all, identifying which are missing from the objective row, and then finding those missing where they have a coefficient of 1. They should actually only exist in one other constraint. And we need this actually to calculate our reduced cost. That's our minus C. Yeah. So if we now change the coefficients, then we basically what we have to do is that we can recalculate our new A matrix by taking the inverted B times our new A matrix. So we basically change these coefficients from x3 to 3, 2, and 1. So in this case, this becomes 3, 2, 1. This is our B, so that's actually this in here at this part. So that's actually here. So we take the B, our inverted B times the A matrix, and we get our new A matrix. And now if we take the cost of our basic variables in the correct order, so starting with the cost of x2, which is -1, then the cost of x6, which is 0, and the cost of 1, which is 2, and then and what you'll notice also here is that x3 is actually not basic, so we're actually changing the coefficient of a non-basic variable, which means that the solution, our current solution, will not become infeasible. So now if we multiply this by the cost this times our A matrix, we'll actually get our Z star. Then we have to basically reduce that by our initial cost vector. Then we basically get 0, 0, 1. And what we'll see in this case is that, of course, our solution is still feasible and it's still optimal. So 0, 0, 1, all the coefficients here remain positive, so it's still an optimum solution. What we can see here also at constraint 1, if we look at our dual problem, then constraint 1 is the right-hand side of constraint 1 of the dual problem. So C1 is the right-hand side. So then if we look at that at constraint 1 for the dual problem, it's basically 3 y1 minus 1 y2 plus 1 y3. So actually that's here. That has to be larger or equal to 4. So that's our new cost coefficient. And basically then if we fill in our y values, which are basically is this. So 3i1, so this is our y star, 110, it's also here, 110, that's our shadow price. So the values for y1, y2, and 3 are basically equal to the shadow price of our primal problem. And if we fill those in, we basically get 5 or is larger or equal to 4. So that actually means that this is still feasible. And still being feasible in the dual problem means it's still optimal with primal. So we could have also done it this way and solved ourselves and basically saved ourselves a bit of calculation time. 3, 4. Yeah, continued. Actually, what now we do is we add an extra constraint, and if we add an extra constraint, like I said in the lecture, the only thing, our solution will still remain optimal because we're not changing our objective value. However, the new constraint might become infeasible. And in this case, also, if you fill in the values, you find that it gets a value of 66. Well, actually, the limit is 60. So we're actually 6 over our maximum value. So in this case, indeed, our solution is infeasible. Well, adding an extra constraint in the primal is equivalent to adding an extra variable in the dual. So what we can also do is then look at the dual and look at what happens if we add an extra variable there. And it's so it's truth much easier to solve. Well, it's this problem actually, because it's infeasible in the primal, it's actually suboptimal in the dual, but it's still feasible in the dual. So both of these statements are false. Well, if we basically then add, if we actually revise the final tableau for the primal problem, we add a slack variable, then okay, what we see in this case is that our slack variable actually has a value of -6. So that indeed means it's infeasible. And if we then use the dual simplex method, basically by taking this -6, looking at which factor here you will run in first, well, it's 2 divided by 11, 1 divided by 3. So actually this is the first one, so 11, what is it, 2 divided by 11? So that's actually the 1 divided by 7. So in this case, what you'll see is that x5, yeah, so 1 divided by 7 is the smallest ratio, so x5 is actually our leaving basic variable, and then if we do all the eliminations, we get the solution, which is not quite as nice as the original solution. And what we see now is that x5 basically is now a basic variable, and x7 is now non-basic, and so here we've applied the dual simplex method. Yep, I hope this was a bit clear. If not, let me know. I'll post this on Brightspace, so you can also have a look there. If you have any questions, run to me, and if I notice a lot of people the same question, then I will show this again, and I'll also put the after deadline on for this assignment. Yes?